which image looks better. Of course, the image number 1 looks better. There's a reason for that. First, let me explain image number 2. If the excitation is performed at a non-optimized wavelength, the emission intensity is lowered, ultimately resulting in low image quality. However, if excitation is performed at an optimized wavelength, emission is maximized, and the highest quality images can be obtained. In general, researchers do not use a light source to optimize for the dye, but rather use a specific filter by appropriately matching the excitation spectrum of the dye. Let's check the examples of commonly used GFP filters and dyes. GFP filter shows high performance in GFP because it is specialized for the excitation spectrum of GFP, but still cannot show the best performance for other dyes, such as Alexa 488 or FITC, DO, Fluo 3, which has a similar excitation spectrum of GFP. However, because custom filters do not exist for each dye, researchers must appropriately match the dye's spectrum to existing commercial filters. TML makes customized excitation possible for each dye. Optimized wavelengths can be selected as 488 nanometer for GFP, 498 nanometer for FITC, and 506 nanometer for Fluo 3. However, there are tens of thousands of different dyes in the world. Using a tunable light source is essential for optimizing fluorescence imaging. Let's prove this using real fluorescence microscopy system using Tunable Mighty Light. This experiment was conducted using Nikon's TE2000 model. All you need to do is connect the liquid light guide and TML. You are ready to experiment. Before starting the experiment, let us briefly explain Tunable Mighty Light TML. Tunable Mighty Light is an LED-based tunable light source that combines real-time wavelength selection filters, high-power white source into one compact size, and has fully automated software control with patented technology. You can check the results of checking the output and spectrum of the light source. Wavelength can be selected in 1 nanometer increments. If you would like more detailed information about TML, please refer to the link on the right. In this experiment, we obtained fluorescence live imaging of the BPAE cell using TML. The maximum wavelength of the excitation spectrum of Alexa 488 phalloidin is 502 nanometer. We selected 3 points in the fluorescence image and measured the change in fluorescence intensity at each point, according to the change in excitation wavelength. We used TML to scan the excitation wavelength from 480 to 502 nanometers at 1 nanometer intervals to check changes in the fluorescence image. In non-optimized wavelength excitation, there was little difference between background noise and signal, and image quality was low. As the excitation wavelength gets closer to the optimized wavelength of 502 nanometer, it can be seen that the signal-to-noise ratio of the image increases. You can see the best fluorescence image quality using an optimized excitation wavelength. As you can see in the image above, the signal-to-noise ratio and image quality in the fluorescence image depends on which excitation wavelength is used. Excitation wavelength optimization affects image quality, and using TML will improve image quality. You will have satisfactory results from experiencing an innovative tunable light source for fluorescence microscopy.